Does it make sense that the resistance, the total resistance in a parallel circuit is smaller than the smallest one? You need to make sure that's a good rule of thumb to follow always.
Because there's more paths.
There's more paths for that current to take. So the resistance is always smaller. Okay? These are the same answers I came up with. Did everybody else kind of do the same thing? So for R total was 1 over R1 plus 1 over R2, which equals R1 in your calculator inverse plus R2 inverse, and inverse the whole thing. That's probably the hardest one to figure out, isn't it? I total, just use 5 volts divided by I total is just going to equal voltage total divided by R total. IR1, remember, Ohm's law is still true regardless if it's across a component or across the whole circuit. So this is going to equal voltage across R1 divided by resistance R1. Voltage across R2 divided by R2 is going to give me the current through R2. Can use, what did you guys use? What equations did you use to find your power across the components?
Voltage times current.
Voltage times current. That's probably the easiest one when you have that voltage, the current and the voltage available. Same thing for that one. What was my other question on here? Do the currents equal the sum of the currents through each resistor? When we sum up all of these currents, is it the same as the total current? Pretty close, right? Pretty close. How about the power? If we total the power here, do they add up to the total power? Yeah, and they should. They should. We'll talk more about that next week. What I want to talk about next is the more complicated circuits, and you're going to apply Ohm's law, the power rule, and know how to get the total resistance, because circuits are never as simple as having them all parallel or all series. So there's always a combination, and it takes steps to get through it. So together, as a class, I want to work through a circuit, and so we can analyze it, and you guys can then apply this knowledge to, I'm going to draw it around, to being able to analyze other circuits. So we have R1, R1 is 20 ohms. R2 is 10 ohms. R3 is 20 ohms. R4 is 30 ohms. And R5 is 15 ohms. And our voltage source is 10 volts. So, just with what you know, what kind of total resistance would you guess? Now you guys can make an educated guess. Anybody?
95.
95. What else? Anybody else got a guess? Dylan, you got a guess?
Nope. I don't like to take a guess. I feel like just solve it.
Take a guess. Take a guess. Got a guess, Victor? Just a guess.
Wait, what's the question again?
A guess for the total resistance.
Oh.
You never know how good you're going to get on your educated guesses unless you do it. Great, you got a guess?
I'm working on
For this one.
figuring it out, so I don't really have a guess. No.
No guesses? You guys don't feel like you have enough to be able to guess?
I mean, I'm sure I do, I just don't want to. Why would I guess when I can just solve it?
Because there'll be times when you're designing and you'll have to kind of figure it out. Oh, I need 50 ohms. How am I going to do that?
I think I'm going to say 30.
30 ohms?
30 ohms. Somewhere around there.
So it looks like we might have just a high and low guess, right? Okay, so let's start the analysis of this circuit. What do we see right to start with? When you guys look at these circuits, what you're going to look for is 2 or 3 resistors that are either in series or parallel. And remember, when we say series, when you leave one, you only go to another one. Now, there's no junction in between. Okay, this should be a terminal here. There's none of those. So is R1 in series with anything?
Yeah, all the other ones.
But when you leave R1, it's not currently, right? When you split, it's not in parallel because it doesn't share a resistance with anything there. If you look at this, let's go to R2. We leave R2. We only go to R3. So those two are going to be in series, right? They're going to be in series. So we're going to label that R2, 3. They're in series. So we're just going to add those together. R2, 3. So it's 10 ohms. R2 is 10 ohms. Let me write R2. Write down the formula first. R2 plus R3 equals 10 ohms plus 20 ohms equals 30 ohms. Okay? And at this step, now I'm going to redraw this circuit. Right? I just combined those together. They're equivalent models. They're equivalent models. Yep.
Can you just change the circuit though by doing that? So when I look at the original drawing, I see nothing but series resistors there. No two of them touch the other 2 nodes or the ends of another resistor.
So they're not in parallel.
So I just added them all up. But then when you did that right there, doesn't that make
Define a series. When we leave this, we break up into 2. It can't be in series. By the definition of being in series, when you leave it, it only goes to one other component.
Okay. Well then, all right. Another question then is when we learned about parallel and AC/DC, he said to be in parallel, the 2 ends have to touch the 2 ends of another.
Correct. So these are not in parallel R series,
Okay.
right? It's a combination. It's a combination. That's exactly the key, to be able to recognize the combination.
Understood.
Okay, does that make sense? He's absolutely right. Parallel, they have to be connected at both ends. Okay? We don't have that here. We don't have anything. R4 is not connected to R3 at both ends, is not connected at R2 at both ends. It's not connected at R1 or R5. Not in series, not in parallel. So we have to piecemeal it apart. We have to take this series, this whole circuit apart and analyze it a piece at a time. Okay? That's what makes it more complicated whenever you get to the combination. So now we said this one is 30 ohms. And whatever those are, I'm not going to copy them all over. Now what do you see? Do we see anything in series or parallel that we can do next for the next step?
I maybe 2 in parallel.
Which 2?
R2 and 3, or the 30 ohm and now R4.
These 2?
Yes.
Are those 2 in parallel? Everybody agree? How do you know?
Because the nodes of R2 and 3 are touching the same 2 nodes of R4.
Now those 2 are in parallel. So R23 is in parallel with R4. This is the common symbol for in parallel with. Okay? So R23 is in parallel with R4. So we can combine those together. Okay? So R234 is going to equal 30 ohms in parallel with what's R4, 30 ohms. So what's 30 ohms in parallel with 30 ohms?
15
How do you know?
Divide the two.
Divide the two. So do you think that's true? Does everybody agree?
If you have,
Go ahead.
yeah, if you have resistors in parallel that are the same resistance, you divide by the number of resistors.
That's it exactly. If I have 10 100 ohms in parallel, I have 100 ohms divided by 10. I have 10 ohms is the resistance. So if they are the same, R1 equals R2 equals R3, you can just divide the value of the resistance by the number of resistors. Okay? So in this case we have 15 ohms. So now I can draw another equivalent circuit. Remember, I didn't say the same, it's equivalent. It's equivalent. This is 5, R5. Now I have this circuit. What are these guys? Series or parallel? Series. You leave one, you only go to one, it doesn't branch off anywhere. You leave this one, it only goes to R5, doesn't branch off anywhere. So now, do I have a green? I do. Okay. Erase these, get myself a little more room. So now I can say R total equals R1 plus R2, 3, 4 plus R5. R total equals 20 ohms plus, what's this one, 15 ohms plus, what was R5, 15 ohms. R total equals, what is that, 50 ohms? Did I do that math right? Okay, so now we can write our equivalent circuit. Voltage source, what's our voltage source? 10 volts. And our total is 50 ohms. Now we can start doing some calculations here, right? We can get our I total, the current leaving the voltage source. How would I calculate it here? What is it? V over R. Remember I told you that Ohm's law you're going to use all the time. 10 volts divided by 50 ohms. What's our total current? How much? 0.2 equals 200 milliamps, right? So we have 200 milliamps. That's going to be true here. 200 milliamps. It's going to be true here. 200 milliamps. It's going to be true here. 200 milliamps. So now we know the current through R1, right? Comes up here, 200 milliamps. Let's back up into here. What's going to be the current through R5? 200 milliamps. It's got to be, right? 200 milliamps. What goes out has to come back. Okay, you can't lose current anywhere. If you're losing current somewhere, you're going to hurt somebody. You guys know how much it takes to really kill a person?
Like 0.5 amps.
5 milliamps. Well, yeah, it does not take much. Current in has to equal current out. So what's the current through R234? 200 milliamps, right? 200 milliamps. So that tells me that I've got 200 milliamps coming in here. How am I going to calculate the current through R4 and R5? we're back at this model. We know there's 200 milliamps. Where's my red? There it is. 200 milliamps. There's a couple ways we can look at this, right? I can calculate the voltage here, what it is. We got 200 milliamps going that direction. You know, I don't know if we're going to do that analysis right now. I think that's enough for today. Just getting down to our R total and what this I total means. I think we're going to stop right there on this analysis, and we'll do more of the analysis next week. R total is really what I want you guys to be able to do the calculations for. I total and the power total. So series and parallel resistance on page 8. I gave you guys some problems to work through. See if you can apply this. Okay, see if you can apply this on problems 1, 2, mostly 3. Try your hand on 4 too if you want.
I got down to 4. You gotta figure it out. The second one. It says the R. It gives me the R total.
While you guys are working on it, I'm going to run back to my office for just a minute. I'll be right back.